All right. So, two homework assignments we need to look at today, right? So we're looking at 2's complement and we're looking at subtraction. So kind of the starting point with this, and we'll look at the Wikipedia thing here in a second that I've given you as kind of starter information. But an issue we have with binary numbers is, well, really an issue we have on computers is how do we implement subtraction? Well, we implement subtraction in terms of addition. So that's what the second homework assignment was. So instead of taking the first number and subtracting the second number from it, what we do is we take the negative of the second number and add it. So if I say 11 minus 10, that's the same thing as saying 11 plus negative 10. Correct? So that's just simple math rules. Okay, so what we need to do is we need to figure out how do we turn a positive 10 into a negative 10. How do we represent that? So let me go here. So a binary complement is such that if we take the original number and we add to it the complement of the other number, we get a net 0. So 10 plus negative 10 would be a 0. So we start off with this idea of a 1's complement. Okay, so this is something that's useful for some digital functions, but it doesn't really provide much benefit for math stuff. So the 1's complement is literally going through every digit, every bit in a binary number and flipping it. So all 1's become 0's, all 0's become 1's. That's the 1's complement. So the 1's complement is the starting point for the 2's complement, right? 2's complement, we then take that and we add a 1 to it. And that's how we get the 2's complement. So if we add a 1 to 1, 1, 1, 1, what do we get? We get 0, 0, 0, 0 with a carry bit. So 2's complement is found by taking its 1's complement and adding 1 to it. So that's kind of the algorithm for that. So I'm going to stop there, because the first assignment was just to say, solve for the 2's complement of a number, right? All right, so we're going to write a program that's going to take in a binary representation of a number, and we're going to get the 2's complement for it. So the first thing is we're going to do is we're going to get the 1's complement. Okay, notice we already have a method in here called addBase that we wrote when we were doing all of our methods for adding stuff. So that's going to come in pretty handy here. All right, so we're going to start off a method here. We're going to say static string 2's complement. It's going to take a string bin as a parameter. Okay, and what I'm going to do is I'm going to first take the 1's complement of it. So I'm going to build a brand new string, and any place in the original string that had a 1 is going to now become a 0. Any place that was a 0 is going to now become a 1. So we're going to say string temp is equal to the empty string. For int I is equal to 0, I is less than bin dot length I plus plus. If bin dot charat I is equal to a 0, then temp is equal to temp concatenated with a 1. Else, temp is equal to temp concatenated with a 0. All right, so we're going to start off with just that. And I'll go ahead and return temp, even though at this point it's just the 1's complement. All right, and we'll see this work. So we're going to say string bin is equal to 1001 system.out.println bin. Then we'll say bin is equal, then we'll just do a system.out.println test.to's complement of bin. So the answer right now should be 0, 1, 1, 0. That's the ones complement, proving that we were able to flip all the bits. Make sense? So there's our 0, 1, 1, 0. We went through every character in this string. Whenever we saw a 1, we made it a 0. Whenever we saw a 0, we made it a 1. That's what this guy does. We're going to build a new string, go through every character of the original string. If I'm looking at a 0, concatenate on a 1. If I'm looking at a 1, concatenate on a 0. Make sense? Now, we need to add 1 to our value. Just so happens, we already have a add base method that takes in 2 strings, as well as the radix, and it adds them. Radix is the base. So I'm going to say, instead of return temp, I'm going to say return test.add base temp 1 base 2. So I'm going to take whatever temp is, the ones complement, I'm going to add a 1 to it. And it'll do all the necessary padding. That's why we have this method called pad bits here that we wrote. So it'll pad that out and ultimately return the sum of this number and a 1. Okay? So if my input was 1001, what should the output be for the 2's complement? That's 0, 1, 1, 0, so it should be 0, 1, 1, 1. Correct? For 2's complement. So there's 0, 1, 1, 1. Questions about that? So this was 2 assignments ago. This was the one that was due last Thursday. So pretty easy. Okay. Now, if you didn't have your add method, you could have written the add method, but adding just 1 to something isn't a really big deal, right? So you could have sort of kind of, not hard-coded, but you could have written a adding 1 function that didn't do quite as much as add base does. Okay, so that's 2's complement. Now, the assignment for today was supposed to take 2 numbers as ints, 2 integers, turn them into binary numbers, subtract the second number from the first number, and return the result. Now, in order to accomplish subtraction, we're going to actually do addition. In order to do the addition, we need to take the 2's complement of that second number. Let's see this. So, we'll just put a slide right here. So bi are I think the example I had in the homework assignment was an 11 and a 10. Is that for the homework assignment? Is that
88 and a 10.
88
Yeah.
and a 10? Okay. CUW. Continue. All right, so we have 88 for the first number. And we have 10 for the second number. And what we ultimately want to do is we want to create the math for 88 minus 10. Okay, but we want to do this in binary. So we need to get the binary equivalent of 88. So binary equivalent of 88 is what? 64 plus 16. It's 80 plus 8. That 64, 32, 16, 8, 4, 2, 1. Okay, so this is the binary version of 88. And then our binary version of 10 is 8s, 4s, 2s, 1s. No. That. 8s and the 2s. Okay? So we want to do this math. We want to take this number and subtract from it this number. But instead what we're going to do is we are going to take the 2's complement of the second number and then add the 2 together. So the 2's complement of this number is what? Well, the first thing we do is we flip all the bits. So that's a 0, 1, 0, 1. So that's the 1's complement. Then we're going to add, so here this is the 1's complement. Then we're going to add 1 to this. So 1 plus 1 is 0, remainder 1. 1 plus 0 is 1. So is that the 2's complement? So we took the 1's complement, then we added 1 to it to give us the 2's complement. Effectively, this is the number -10. Now, how do we know it's a negative number? Because of the 0 on the front. If we're told a number is currently represented in 2's complement form, and it starts with a 0, it's a negative number. That makes sense? We still have to be told that the number is in 2's complement form. We have to know that. Because at a glance, we don't know the difference between a normal binary number and a number encoded in 2's complement. Unless somebody tells you.
The other way around, where if it starts with a 1, it's negative.
Yes. A 0 is positive, a 1 is negative. What did I say? I said, oh. Yes. Wait, hold on.
You need a 0 on the front of your positive 10.
Who?
Your positive 10 right now is a negative number.
Yes.
Your binary representation of 10 is in 2's complement form is a negative number. Because there's a 1 on the front. No, up. Your 10. The 1010. That's a negative number in 2's complement. Because it's got a 1 on the front.
That would be.
This isn't the 2's complements, though. This is the original.
It would be a -8 in 2's complement.
Yeah, this is the original value, 1010. So that's the binary number 10. 2's complement would then be 0110.
No, but you need a 0 on the front, so then when you take the 2's complement, you get a 1 on the front for your negative number.
You have to add a 0 to the front before you do 2's complement.
What? What are you talking about?
You have to add a 0 on the front of your 1010.
So
when you switch it around,
For signed numbers.
Yeah.
To represent it as signed numbers as opposed to unsigned numbers. Yes. So at this point, when we did our 2's complement, we made it work, and I think it's in one of these things. Lift it up more. Because 2's complements can be used to represent signed and unsigned numbers. And only in the signed number do we look at that extra bit on the front. And this has to do with that idea of our signed bit here. So in Java, if we have signed numbers, that's why, like for instance, like in Java, a byte is an 8-bit signed number. So it's plus or minus 2 to the 7th power. Because one of those bits is used to control the sign, keep track of the sign. Make sense? Okay, so right now, our 2's complement method just does a global 2's complement. So this actually assumes unsigned. Correct? That's what this currently does. Is it assumes we're not dealing with signed numbers. It assumes we're dealing with unsigned numbers. Because what you want to do, here's my slide here. you wanted to put a 0 in front of that, a sign bit, saying this is a positive 10. Correct? Okay, so you want to say this is a positive 10 now. So to take the 2's complement of this, that's a 1, that's a 0, that's a 1, that's a 0, and this would be the 1 to represent, well, at this point we're not done. It doesn't represent anything at this point because it's in 1's complement. Then we're going to add 1 to that. So this is going to be a 0, carry the 1, a 1, 1, 0, 1. And because we were told this is represented as a 2's complement of a signed number, we know that this digit right here is dealing with the sign. Correct? So a 1 is a negative number. A 0 would be a positive number. But whatever this digit is, this bit is, has no impact on the value after it. It just tells us whether it's a positive or negative number. Yeah.
If it's unsigned, what's the point of 2's complement?
If it's unsigned, what's the point of 2's complement?
That you wouldn't be able to tell if it's negative or not.
Unless, well, what do you mean you wouldn't be able to tell if it's negative or not?
Because isn't the point of 2's complement to subtract? So if you're going to
A
subtract,
use of 2's complement is to subtract. But 2's complement also gives you the antithesis of another number. So I think I see what you're asking. So if I took that, let's just do this as an unsigned. If I do this and I take the 2's complement unsigned of that, we get a 0, 1, 1, 0. Like that. And let's add those together. So that's a 0, 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, 1 plus 1 is 0 with a carry bit. So still is the antithesis. Still comes out to a 0. So with 2's complement still gives you a 0, you have the extra carry, but that doesn't drop down because it's, remember when we dealt with carry registers, when we wrote our thing, we just had a single carry bit that we just kept going. You don't necessarily drop it down unless you're doing math with it for a final solution. So you're asking what's the purpose of 2's complement unless we're doing subtraction. I think you could make the argument there isn't much, but it still is valid for unsigned numbers to be represented in 2's complement. It's a valid representation. I'm sure there are some uses. I can't necessarily come up with one. I mean, the way we're going to use it is for subtraction, to represent it in addition. But 2's complement can be used for unsigned numbers. But to your point, it probably doesn't make sense. Okay, so we have our 2's complement of our number for 10. And we have our 88. But now, how do we represent this 88 in order to do addition? How do we know this is a positive number? So I'm going to do my math. 88 minus 10 should give us an ultimate value of 78. The binary equivalent of 78, positive 78. Correct? So if I have this number, which represents a negative 10, and I want to add a positive 88 to a negative 10, do I represent 88 like this, or do I have to modify our 88? Okay, what way will we modify it?
Stick a 0 on the front.
Stick a 0 on the front. Why?
Because the 0 means that it's positive.
Okay, so we're not encoding it in 2's complement. We're not taking its antithesis. We're just representing it as a signed number by adding a bit onto the front. Okay, so we're not going to modify our 88 in terms of its complement. All we're doing is we're saying, I want to treat this binary number as a signed number. This is the number positive 88. So we're going to put a 0 on the front, indicating that this guy is a positive 88. Make sense? Then we have this number, which is our negative 10. And now we can do addition with those. So when we do our addition, we're going to pad it. Just get a clean text box here. So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Carry the 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. So we get this value. And this value is what? This is the ones place. The 2s, 4s, 8s, 16s, 32s, 64. So this is 64 plus did I do that right? 1s, 2s, 4s, 8s, 16s, 32s, 64. So this is 64 plus what? 32? What's that? 96 plus 16 plus 8. So now we're at 104 plus 4, 108, 110. So this is the number 110. Is that what we're looking for? What do we need to do? That's not the right answer, is it? What's this number minus 1? Is this number in 2's complement form? I want a 78 out of this. How do I make that happen? But
Why wouldn't you put the 1 to designate if it's negative or not in the front of the, yeah, right there. Why wouldn't you put the 1 there?
oh, it's a good question. Why wouldn't we?
I mean, we're supposed to, right?
We should. We should pad this guy out before we put its sign on there. That's the number negative 10. Is that correct? Only the far left bit?
Well, no, because that the way it works is the one, whatever one, you know, if it's farthest left, it still takes that value. So that's, I don't even know what place it is, but I'm just gonna say it's negative 256 is what that comes out to be. You add negative 256 plus the rest of them. It's just that bit is negative. So that's when you do 2's complement. I know, like I saw some things online where it has you also input the number of bits because it's important because you can represent the same number multiple ways in 2's complement, just differing in numbers.
Right, but as long as you have both numbers in the same number of bits, it shouldn't make a difference.
Yeah.
For us, for what we're doing. So the question is how do I represent a negative 10? This was our 2's complement of a 10, correct? This number down here. But in order to do my math, I need to put it up there with this guy.
You can take the 2's complement of 10 with like a bunch of padded zeros on it before you do the 2's complement, have 10 with a bunch of padded zeros.
Okay.
Then take it.
So what you want to do is you want to know, so here's our 10, our original 10. You want to know that we need a total of 8 bits?
Yeah, sure.
Okay, so you want to actually put,
but then not add the 0 on the front like we did before because it's already got 0 on.
we're going to add the 0 on it. So
Yeah.
you want to start with this, then add the 0.
Yep, correct.
Okay, so you want to start with this so both of these guys are in the same format, same length for our starting point. Then we're going to take this number, which is our starting point, and what do you want to do to the front of it?
Throw a 0 on it.
Throw a 0 on it. What does that represent?
Still represents 10.
Okay, still represents a 10. Now we're going to take the 1's complement. So the 1's complement of this, just modify this one, is 1, 1, 1, 1, 0, 1, 0, 1. It's the 1's complement. Okay, 2's complement is going to be that number plus a 1. So that is 1 plus 1 is 0. 1 plus 0 is 1. 1, 0. 1, 1, 1, 1. That's the 2's complement. Okay, so a negative 10 is that. Right? When we do the math, do we incorporate the signs into the addition? So now I'm adding these, just like I did before. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1, we'll just go through it. 1 plus 1 is 0, carry the 1. So we have an extra carry bit over here now, right? All right. But this is our number. What number is this? This is the 1s, 2s, 4s, 8s, 16, 32s, 64s. So this is 64 plus 8, which is 72, plus 4,
76.
76,
78.
plus 1, or plus 2 is 78, plus 0. So this is a 78. How do we know that it's positive 78? Because that's a 0. We know it's a signed number. So we have to have, in order to do subtraction through addition using 2's complement, we have to use signed numbers. Right? So we know this guy's a signed number. We know that it's a positive number because of the 0 there. The rest of the number reads. If this was a 1, that 1 would not would not have an effect on the value. So the actual value stored here is that. This extra bit is strictly for sign. 0 is positive, 1 is negative. Strictly. We don't use that for value. So, if this is the 64's place, this isn't the 128's place.
In 2 complements?
Huh?
In 2's complement, we don't use that for the value?
Oh, what do you...
Because you do. That's how it gets its negative value, because everything following that cannot add up to that. So that's how it is negative. That's the negative bit. If it's or if it's 0, you could just look at that as being 0 times whatever place. It's negative that times 0, I guess.
Right. So what if I had this? Let's just change our number here. let's make this that. What value is that?
How many? See, is that 8?
1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s.
So that's negative 128 plus 64 plus the rest of that stuff.
Okay, so negative 128 plus 64 plus that's 32, that's 16, 8, 4, 2. Negative 50. Okay. But did we count that in the math? We used it as part of our thing, but it changed. This was the 1's place, this is the 2's place, this is the 4's place. 8s, 16s, 32s, 64s. This is the 128's place. But because there's a 1 there and it's a sign bit, you incorporate it as a negative 128 into your number. Why is it a negative 128?
It's just how
Besides, that's how it works. What's the argument for that being a negative 128? Because if there was a 0 there, did we still do the same thing? Did we still add in 0 times a negative 128? Yeah, it's same math.
Yeah.
Same math, right? So when we had this guy, this is, to break this down, this is 0 times negative 128 plus 1 times 64 plus 0 times 32 plus 0 times 16 plus 1 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. Oh, that's on. So that is how this math works.
3 needs to be a 2.
Oh, thank you. I think I said it right, didn't I? Just typed it wrong. So 0 times negative 128 plus 1 times 64 plus 0 times 32. So this gives us a positive 78. This number is the exact same thing as this number, except we have a 1 times a negative 128, which was the negative 50. Is that how the math worked out? What makes this the negative 128th place as opposed to the 128th place? It is the signed bit. We have to know that's a signed bit in order to do it this way, right? We must know it's a signed number. Signed numbers always have the far leftmost bit being a negative number. And this gets down to where we were talking about, as long as the numbers are the same length, equivalent to each other from the get-go, we can treat them the same. We don't have to know, we don't have to deal with them in bytes or words or something like that. In computers, they actually would deal with them in 16, 32, 64 chunks like that to make it faster. But from our perspective, just doing it hard by hand, we don't need to know that, as long as we know everything is equivalent. The signed bits are in the same column. It's the important thing. So with both these numbers, the signed bits are in the 128th place. Because it's a signed bit, it's always negative 128. And whether we make it a negative number or not depends on what? Well, depends on whether or not we've added in a big negative number. In this case, a medium-sized negative number. Whether there's a 0 in the negative 128th place here or a 1 in the negative 128th place here. Can we have a 1 in the negative 128th place and still come out with a positive number? Is that possible? What would that number be?
-1.
-1.
All ones are always -1.
Okay, so this is 64 plus 32 plus 16 plus 8. Yep, that's going to give us a weird number. 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 plus a negative 128, which gets us a -1. So, if you have a 1 in the far left, that number will always be negative. The reason it's negative is because this is 1 times the -128th place. Okay, that's why the math works. Not just because it works. It works that way because we know it's a signed number. We know the far left bit is the sign bit. And that's always the negative, whatever place that is. That make sense? So, when we had this number, this was our math, right? We knew this is a signed number because we did 2's complement addition to calculate subtraction. We knew this was a signed number. So we knew this 0 in the far left thing represented that it was a negative number. I'm sorry, represented that it was a positive number. 0 is positive, 1's negative. 0 represented it was a positive number. That's how we can tell it by looking at it. Can we ever have a negative number if you have a 0 on the front? Never have a negative number if you have a 0 on the front. In signed 2's complement. You can certainly have a negative number if you have a 0 in the front. Something else we'll look at, we might not look at actually, deals with decimal point values and how they're stored for fast multiplication. You can actually have a negative number with a 0 in the front, but that's not related to this. So from our intents and purposes, all positive numbers will have a 0 in the front for signed numbers. All negative numbers will have a 1 in the front for signed numbers. But what makes them positive or negative is the exact same math we've been doing all along, except we treat the signed place as the negative, whatever place that is. Does that make sense? Okay. So, when we take our 2 numbers, we're going to convert them to binary. Just remember, we're writing a method here. Static string subtract. Is that what I said to call it, or did I say? Int val 1, let's call it int a and int b. Int a, int b. First thing we need to do is we need to convert a and b to binary numbers. Very first thing. Do we still have the code for that?
It's in converter.
Oh, it's in converter? Okay. So we'll say string bin a is equal to converter dot decimal to binary of a. String bin b is equal to converter dot decimal to binary b. Okay? Now, we need to have bin a and bin b being the same length. That's what we did right here. Make sure these guys pad out to the same length. So, what we're going to do is we're going to have an int max length is equal to math.max bin a dot length bin b dot length. I've shown you that before, right? The max. So this is a built-in function in math that just tells us which is the largest value between 2 integers. Which I think it takes in longs, but whatever. So now we know max length is the length that we want both of these strings to be in. So we'll say bin A is equal to test dot pad bits bin A max length. So for one of these, it's not going to do anything, right? We already know it's the correct length. So if bin A is 8 bits and bin B is 4 bits, when we tell it to pad bin A out to 8 bits, it's just not going to do anything. It's just going to leave it at 8 bits because it's already there. Bin B is equal to test dot pad bits bin B max length. Now we know that bin A and bin B are the same length. So we've accomplished this aspect. Now we need to take bin B and get the 2's complement of it. So we'll say string bin B2 is equal to test dot 2's complement bin B. That gets us the 2's complement of that. So now we have that value. This guy right here. Now we'll add bin A and bin B2. This is the 2's complement version of bin B2, giving us our final answer. Bin A, bin B2, this guy's in base 2. We'll return that answer. Uh, 88 and 10. And we're hoping it gives us this number right here. Front row. 88 and 10. 80. Oh. So should be 1, 0, 0. Oh, my answer just had the extra carry bit.
Yeah, it's just showing the carry bit.
Yep. So this is the answer. 1, 0, 0, 1, 1, 1, 0. We had the extra carry bit that happened from the math, but we throw that out. So really, our add right now isn't real compatible with this because we can't just immediately cut off the left bit. Huh?
Isn't it still a signed number, so it shouldn't start with a 1 if you're getting 88 minus 10?
Well, the problem is that our current addition just drops down the extra carry bit.
You could always lop it off.
But I don't think we could just automatically lop it off. Because then you might be assuming that there was an extra carry bit when there wasn't. We're only, if you look at our addition, I'm almost positive I remember this. If you look at our add base,
Well,
we look at the overflow.
You could say that if the returned answer is longer than your than the number that than the length of your first number, you could just lop off the front, because then you know that carry bit got appended to the front.
True, but here's the reality of it. Since in our computers we're going to have 2 different versions of addition, we're going to have signed and unsigned addition. Realistically, there would just be a magic trick in the CPU. Add base signed like this, where we would never deal with the carry bit. The carry bit just becomes a casualty of war, if you will. So in that case, we can say add base, call it signed, And then we get our correct answer. We just let the carry base, the carry bit, just die with it. So the carry bit becomes wrapped into the signed math because it's something that's left over. Does that make sense? I think this works.
I mean, it still has a 1 on the front.
Oh, did it not?
You're missing a 0. It needs 1 more 0 on the front.
Oh, because of our pad.
Can you just say, like, if it's longer than the max length? If it's
That wouldn't be the way. Well, you wouldn't have access to max length there. You could do it in here. You can come into subtract. You can just get the answer.
the answer is +1.
String answer is equal to that. Then you could say if answer dot length is greater than bin a dot length, and return answer dot substring 1. Otherwise, return answer. And then you can just use our normal add base. I really don't like that solution though.
You have to make sure that before you take the 2's complement that you don't have a 1 on the front of your binary number.
Actually, we need to go, it's really the other direction we need to go right now. We're getting this number, but without the 0 on it.
Yeah, you need to add a 0 to your numbers before you take the 2's complement.
Let me do something here though real quick, because we're just doing add base. That's giving us the carry bit. Yeah. Okay. So we did need to do the, I really don't like that solution though, but I guess it's reasonable enough. But now before we, so now this gets us the correct answer, but we're missing a 0 in the front for the sign. Correct? But can we just pad we can't just pad a 0.
No, for your original binary numbers, if you put a 0 on the front of both of them, if there's a 1, if they start with a 1, before you even go into taking the 2's complement.
Oh, you want to doctor the original numbers more.
I want to doctor the original numbers and just add another 0 if either one of them has a 1 as their first number.
I don't like that either.
It works.
Yeah, it would work. I mean, the reason I don't like that is we are now arbitrarily taking up more memory. And if you think about the inside of a computer, you wouldn't just arbitrarily take up more memory just 'cause.
I see your whole entire 2's complement method.
Here's 2's complement.
I think it might be because we're not adding the 0 to the front of what we're taking the 2's complement of in that case, if that makes sense. Because that'd be like when we were kind of
We haven't done the first step of 2's complement. We need to tack a 0 on at the beginning for 2's complement.
Because it'll make it 7 and then make it 8, and then it'll have the extra 0.
Right. So what we could do here is we can say temp is equal to a 0. Nah, that's not right. That's not right. That's not.
Do it right before.
We would say bin is equal to the empty string concatenated with bin. That's our 0 for the 2's complement.
The empty string.
No, the 0.
Yeah.
Again, do as I say, not as I do. So we're going to concatenate on a 0 onto the front of that whatever was passed in.
Yeah.
and then we'll do our normal 2's complement.
Yeah, try that right now.
Let me see where we left this off in here. We're not, we're subtract. Okay, so that works there. And will it work for negative numbers as well? Let's say 88 minus 98. Does. I think that's the right number, right? So this is 1s, 2s, 4s, 8s, 16s, 32s, 64s. So that's a negative 64 plus a 32 plus a 16. So 4 plus a 2 is a negative 10. Yep. So negative 10 is the answer we should get for 88 minus 98. Yeah, you were right. And the thing is, we said that too. Right at the very beginning when we started talking about 2's complement, we said we need to add the 0 onto it. And then when we implemented 2's complement, we didn't put the 0 onto the front of it like we were supposed to. So our error was back here. Okay, so subtract works in terms of addition, but we have to know we're dealing with signed numbers. In the end, minus our hiccup there, we see that subtraction was actually fairly simple. These first 2 lines are just converting 2 ints, 2 decimal numbers, into binary. Where in a computer, they're probably already going to be in binary. So we can almost throw those out. If we had made these take in binary numbers, it would be different. These next 3 lines are all about padding, making sure things are the same length. Again, if we had registers that were, let's just say 16-bit registers that were filled up with binary numbers, they would already be the right length because they start off being filled with zeros, and then we fill them in with the right values. So we wouldn't even need, if we're thinking about this in terms of what would actually be inside of our computer, we wouldn't even need those next 3 lines. They'd already be padded. All right? So really, this guy starts right here. Take the 2's complement of our second number. Then add. We're going to have an add function. That's one of the magic tricks that our CPU knows how to do. Add one register to another register. Okay, so you have 30. We'll load those 2 numbers into 32-bit registers. So if we're thinking about this from a computer perspective, we might, let me just give ourselves a little block. We might say something like move into AX bin A, move into BX bin B2, AX and BX being, in this case, they're actually both 32-bit registers, but whatever, just roll with it here. So we're going to move these 2 values into hardware registers. These are built into the CPU, so we're kind of broaching the subject of assembly language right now. So we're going to move this value into this hardware register, move this value into this hardware register, then we'll do a add CX, AX, BX. So add is a function that takes in 3 parameters. It takes in where do we want to store it, and what are we adding. Final result will be in CX, and then we can return CX, CX being our answer. That makes sense? And realistically, this is probably called like add signed or something like that. Because there is a separate add function for signed numbers versus unsigned numbers for performance. Something you'll talk about in the, I referred to it a little bit earlier, something you'll talk about when you take the senior seminar class with Dr. Locklear, the first class, 491? I think 491. Is that right?
I think 490.
490 and the 491's with me, the project. But in 490, you'll talk about fast multiplication. And you'll look at some of the, and you've probably seen some of the questions on at the CS get-togethers about fast multiplication. So one of the things you'll talk about in there is fast multiplication and how CPUs have a magic trick that does multiplication really, really, really fast. Okay, so we have these special purpose things inside of our CPUs that increase the instruction set of our CPU. So our modern day CPUs have a very large instruction set, and we've actually seen, except for our mobile devices these days, we've seen it move away from reduced instruction set processors, RISC, RISC processors. So old Macs used PowerPC chips that were reduced instruction set. We do see it today in our mobile devices that have ARM-based chips, ARM. Those are a reduced instruction set chip. Now, reduced instruction set just means that the developers of the chip tried to minimize the number of magic tricks that the CPU knows how to do in order to accomplish everything it needs to accomplish, general purpose tasks. Why would we want to minimize the number of instructions in mobile computing? What's an instruction on the CPU? Okay, well, and this kind of segues into where we're going next as well. If we think about our processor, I've always talked about our CPU as being kind of a collection of magic tricks, right? Each one of those magic tricks is implemented how?
By calling them.
Well, that's how we call the magic trick, but how do we implement it? How do we build it?
What hardware? What do you?
At some point, I made a comparison between software programmers and hardware programmers. That we implement hardware in terms of gates, AND gates, and NOR gates, and XOR gates, and logic flips, and things like that. A bunch of crap that ultimately turns out to us writing a computer program, what we think of as being software, with a bunch of hardware. And there's a flow-through effect. We go through this, then we go through this, then we go through this, then we go through this, and ultimately it spits back out. We have our answer. So if we think about our CPU and every magic trick our CPU does, think of each of those magic tricks as kind of like a method. You know, we're writing methods for all these different things in Java. Each of those magic tricks is a method, where the method is made up of a bunch of pieces of hardware. It's small scale. We use very large scale integration, DLSI, for our hardware, which tries to compact everything in there in small of a space as possible. But the more magic tricks our CPU knows how to do, the more space it's going to take up, right? So why do you think our modern mobile computing devices are moving towards reduced instruction set ARM processors and away from, let's just call it, expanded instruction set processors like Intel chips?
So we can make a giant phone screen.
So the devices stay the same size, but more of its screen than just space for the processor. So really, the punchline is we want our processors to be as small as possible.
So we put other crap in there.
Put other crap in there, whatever, right? You know. Well, and we are. I mean, so that's when we think about our smartphones. When I say mobile computing, the first thing that comes to our mind is maybe smartphones. But realistically, there's all sorts of other things that go into this. For instance, I was watching a documentary the other day that talked about surveillance stuff, and a lot of the things that's in the news these days deal with drones, right? So you look up at the sky, you see one of these helicopter-looking things. That's what we think of as a drone. Well, there's some really cool technology out there where they're catching insects and augmenting insects with stuff. And then even using electrical signals, controlling that insect to some, and this is real. Isn't that kind of fascinating? You know, they'll like catch like a beetle and put a couple of probes into its brain and then deliver some signals. And it's got cameras and microphones and stuff like that. And you just release it into the Pentagon, or something like that.
Thread the wire down its antenna.
Yeah, whatever.
There's a YouTube video.
So we have this. Say this again.
There's a YouTube video on it.
Oh, you've seen it. Okay. So you can say this is real. I'm not just making this up. So the point is that for certain applications, we want to move towards a really, really reduced instruction set. Those are very special purpose processors. when they build that hardware to send the moth in to well, then probably not the moth people try to kill. People tend to ignore flies as long as they're not too annoying, right?
Butterfly would be perfect. Look at the beautiful butterfly.
That's right. Yeah, but they would probably not talk about the stuff they're trying to
Sure.
you know, they'd be talking about butterflies. Yeah, what you really need is you need the fly sitting on the table over in the corner and bothering nobody and just capturing everything. But the point is those are very special purpose computers where they can put a minimal amount of hardware on them, a minimal amount of magic tricks it knows how to do in order to fulfill its task. We take this even a step farther, the direction that we're starting to go with technology. How many of you have heard of nanotechnology? Nanotechnology is really cool. There's a really good book. I think it's called The Invisible Machine. I think I've referenced it in some other classes before. I think it's Kurzweil. Isn't it called The Invisible Machine? It's Ray Kurzweil. I don't think that's him, is it? Maybe it is. This is actually a good book too, The Age of Spiritual Machines. When computers exceed human intelligence, kind of a neat book, but that's not the one I was referencing here. I really thought it was called The Invisible Machine. Whatever. But in any case, whatever the title of the book I'm referencing is, I'll try to come up with it at some point. But talks about kind of the future of computing, but it's the book's probably about 15, 20 years old. So you actually see some of this guy's predictions come to fruition. But he talks about how, he really gets into nanocomputers and how we're going to eventually have, computers that encompass all the power of all the computers in the world that we have today. So take every computer we have in the world today, all the horsepower that thing can have, and imagine it floating invisibly in front of you at the molecular level. Think about where we're at today in terms of thinking about wearable technology and stuff like that. And what if you didn't even have to wear it? It was just there. Or it was, microfibers were sewn into your clothing that, you had some sort of Bluetooth receiver inside of your skull that, just got all the pictures or, whatever it is, whatever signals it's sending, where it really just becomes ubiquitous around us. Isn't that kind of amazing?
The II.
The II.
Revolution, they have nanotechnology that I guess started reproducing on its own or expanding on its own. It would suck all the electricity out of the air and it caused everything to break down, everything to shut down and put people in the Stone Age. And they didn't know what happened or how it happened, but they knew it was the nanotech that decided there was a bug in it that caused it to replicate uncontrollably, and you couldn't see it, but you'd be breathing it in.
Yeah, and I really think it's also going to be very related to the future of medicine. This kind of becomes a problem-solving type thing and a very much a human brute force approach. So, and I know there's a bunch of research with nanotechnology now with cancer. What's cancer? Cancer is an overgrowth of cells, right? So we keep searching for a cure for this type of thing to keep your cells from having an overgrowth. Well, what if we just put a bunch of nanobots inside your system and we just said, oh, you have an overgrowth of cells. We'll teach these nanobots how to attack those cancerous cells and we'll just destroy them, keep them at bay indefinitely. Still have cancer, but you're not going to die from it.
So they override and just start eating the rest of the body.
Yeah, you got to make sure they're pretty good at telling the difference between a cancerous cell and a non-cancerous cell. Otherwise, we'll just be killing them quickly.
Don't go straight.
We'll just be gutting them for later.
But really, the future of medicine might be something like that. You think back to this might be a little bit before some of your times, but maybe you've seen it when some of these movies where they shrunk people down to go do medical procedures and stuff like that. put them inside of other people's bodies. Well, that's putting a whole human being inside of, huh? Right. But in any case, I really think that we're going to get to that point. And we already have to a certain extent. So, for instance, this relates to, my last week. I don't know why I didn't get the good technology, but sometimes when a doctor needs to take a look inside somebody, there's some technology now where you actually swallow this pill. You swallow it, and it has a camera on it, and it just, as it goes through your system, it's beaming back video. So it's completely non-invasive.
It's a lot to beam through.
You just pop. Well, that's true.
Probably why.
You just pop a pill. But the point is that these things exist, so they don't need to. It's a non-invasive way of doing stuff. So I really think that's kind of the future of stuff. But the idea of that nanotechnology kind of takes this idea of mobile computing to the extreme. But kind of getting us back where we were going with the reduced instruction set thing. When we think about our computer processor, we really want to draw some parallels to the computer processor and programming languages. When we first learned about programming languages in one of our other classes, we said, oh, there's 3 different kinds of programming languages. We have high level, low level, and machine language. There's 3 different kinds of programming languages. We have functional language, we have procedural languages, we have object-oriented languages. There are 2 kinds of programming languages. We have general purpose languages and we have domain-specific languages. General purpose languages being like Java and C# and Objective-C. These are massive languages that have a whole bunch of features in them that allow us to do a whole bunch of stuff whether we use them or not. I've used the example before. I've been writing Java since the language came out. And I bet you I've used less than 10% of the entire language. There's all sorts of crap built into Java that I've never had a use for. Okay, just like, you go to Home Depot and there's a zillion tools in there and, you only own a subset of them because you've never had a need for random tool X that hasn't applied to a job that you've had to do. So when we talk about computer processors, we really want to think about them at a laptop or a desktop level as general purpose processors. And to a certain extent, even at a smartphone level, we still want these to be general purpose, at least to a strong extent, because we've really moved our computing, our productivity towards these, correct? I mean, we still have a need for our laptops or our desktops, but every single year, more and more of us are doing more things on these types of devices. We haven't put these down yet, but it's shocking how much we accomplish on these. Well, as we become more mobile, as more of our computing becomes mobile, the need for large general purpose processors that do a zillion different things gets put to the wayside. Part of that's because of miniaturization. We want to have our devices fit in our pockets and stuff like that. Another reason is battery life. The less magic tricks our CPU knows how to do, the smaller the CPU is, very likely the less power drain the CPU has, that kind of stuff. So we have all these conflicting goals. So that's why ARM processors have really kind of taken off in our non-power tethered devices that are running off battery, because we're able to only put features into the processor that are, that make sense for the device being mobile. And even having said that, if we look at an expanded instruction set processor like the Pentium processor, which is now many revisions newer with Intel, their Core i7, let's say. When you look at that, when they talk about an expanded instruction set versus a reduced instruction set like the PowerPC processors that Macs used to have, it's not that the Intel chips can do more than the Mac processor can do. It's that in order for the PowerPC chip to accomplish the same thing that an Intel chip accomplishes, it might have to call upon more of its individual magic tricks. I'm going to do this move, then this move, then this move, then this move. Where it's possible with the Intel chip, they might say, oh, well, since we do that move often, we're just going to build it into its own magic trick. Do the move. that make sense? So there's quite a bit of overlap in some of our more modern expanded instruction set chips because certain things get called all the time, so why not be able to do it in one line of assembly code rather than 4, as an example. Well, when we get to our mobile devices, we might decide, okay, well, we're going to do it in 4 lines of code because 4 lines of code takes up less space than hardwiring an extra feature into the processor that mimics those 4 lines of things. Unless something is being used constantly, we're not going to take up space for a little convenience when we can accomplish the same thing through software. Part of that gives up some performance. So one of the reasons for the desktop computing, one of the reasons desktop computing has kind of adopted the power-hungry Intel chips, which do draw more power than the reduced instruction set processors did, which do have a physically larger size, or at the very least are reliant on more and more technology to squeeze more and more into the same size chip. That's why we're starting to hit that limit right now. That's why we keep just adding more cores. Like we can't put any more on here without it conflicting with each other. Wires touching and stuff like that at the molecular level. So rather than changing our standard and making our processors physically larger, we just throw more cores in there and hope we have enough cooling to dissipate the heat. So having said that, when we get into our mobile platform, typically we don't think about performance on our mobile devices unless we're looking at a device that's 2 or 3 or 4 years old, right? When you buy a new phone, yeah, all the commercials talk about it has the blah, blah, blah Snapdragon processor. That's a cool name for a processor, isn't it? The Snapdragon processor.
A little better than the A8.
Yeah, right, exactly. If you had a choice between buying a processor called the A8 versus the processor called the Snapdragon, which would you pick? It's like a Snapdragon, right? Okay. Both of those are ARM processors. Apple's A8 chips that they make, it's an ARM processor. They say it's their own silicon. They make their own chips. If you roll back the clock about 4 years, you see Apple bought a semiconductor company, put the Apple logo on it. Now that company makes Apple's chips by Apple. It's a company Apple acquired that makes chips. Okay, Snapdragon chips are made by somebody else. So a lot of these Android devices have the Snapdragon chips in them. Whatever. Bottom line is they're both ARM-based processors, reduced instruction set chips. But when we think about them, the commercials talk about it having this blah, blah, blah gigahertz, 1.6 gigahertz, quad-core Snapdragon processor. I think there's even one that has an octa-core, 8 cores in it. Whatever. But the punchline with those is that those become selling points for consumers. But for us technologists, when we think about our mobile hardware, we typically don't think about one phone being faster than another phone unless it's several years old and the newest software feels sluggish on it. You know what I'm saying? If you have last year's iPad and you have this year's iPad, which has newer hardware in it, and you're running their newest operating system, iOS 8, you probably won't really feel the difference. Both of those are going to be fast. If you have an iPad 2 from several years ago trying to run iOS 8, it might feel sluggish. Now you're feeling those years. Okay, but when we think about our mobile computing platforms, we're less concerned about horsepower, speed, and more concerned about battery life. We want enough speed while maximizing our battery life. We're probably not willing to have more speed than we need. More speed than we can appreciate is maybe the better way of putting it, at the cost of half the battery life. We'd rather have longer battery life and less speed than anything else. That make sense? So this idea of reduced instruction sets moves us towards the idea of domain-specific chips. That's where I'm making that comparison between programming languages and hardware. Now, as we keep going, let me just, in our last minute here. So I want to start getting into writing some of these gates and stuff. Okay, so we're just about done with this stuff. And then I'd like to get into some assembly language stuff and some designing methods at the hardware level. So we can kind of round it all out and see how all the same stuff we've been doing works in other situations. All right? I will see everybody on Thursday.